Let's have the solution of example 26, letter E. So let's open our open board. So as you can see here, we have this one. Example 26, letter E. Okay, this is the solution. So let's recall the given first. We have a sub n plus 1 is equal to n plus 1 times the quantity a sub n minus n plus 1 for n greater than or equal to 0 and a sub 0 is equal to 1. So let's see if we are correct. N greater than or equal to 0, a sub 0 is equal to 1. Okay, so first is let's have we are going to let a of x to be equal to the summation of a sub n x to the n over n factorial. So we will solve this problem using exponential generating function. Okay, use exponential generating function, EGF. Okay, but maybe you can try it at home using ordinary generating function if it will work. But as of the moment, let's try to solve this using exponential generating function. So let's try to expand. I didn't expand this one before, but let's try to expand this. This is x to the 0 over n starts at 0. We have 0 factorial plus a sub 1 x to the 1 over 1 factorial a sub 2x squared over 2 factorial and so on and so forth. This is a sub n x to the n over n factorial. Let's move somewhere here, plus dot. Okay, and this is the period. Okay, so that's the expansion. Then as before, we are going to multiply the given by you can multiply by x to the n, but for this problem n plus 1, let's multiply both sides by x to the n plus 1. Okay, it depends upon the situation. So first is let's have to simplify this first. A sub n plus 1 is equal to this is the recursive formula. Okay, let's multiply n plus 1 a sub n minus notice that uh, this one here can be expressed as a sub n minus n plus 1. Okay, and not n plus 1, it's n minus 1. Sorry, n minus 1. Okay, if you multiply negative 1 times n, we have negative n. Negative 1 times negative 1 is positive 1. So what happens here is we have n plus 1 times n minus 1. Okay, so just distribute. Okay, this one here and that one. Okay, and then you can multiply both sides by x to the n plus 1. Okay, it depends upon the situation. This becomes n plus 1 a sub n minus n plus 1 n minus 1. We are going to multiply both sides by x to the n plus 1. Okay, so here we have multiply by x to the n plus 1 over n factorial. So since we are dealing with exponential generating function, okay, and then we have to sum overall where n starts from 0. So this will become summation of a sub n plus 1 x to the n plus 1 over sorry, this should be this should be, since we are what do you call this one, multiplying both sides by x to the n plus 1, the denominator must be n plus 1 also. N plus 1 factorial. N plus 1 factorial. Okay, so this will become n plus 1 factorial. N starts from 0 to infinity, and we are going to distribute the right hand side, this one to here and also this one here. Okay, so this will become n plus 1 a sub n x to the n plus 1 over n plus 1 factorial. N starts from 0 to positive infinity, minus we have summation of n plus 1 times n minus 1 times x to the n plus 1 over n plus 1 factorial. N starts from 0 to positive infinity. Okay, so this becomes the idea here is to sum over all for n greater than or equal to 0. Okay, so let's simplify first. Let's simplify. Notice that the first term on the right hand side, if I don't know if you recall the definition of the factorial. Let's put it somewhere here. Recall that n factorial is equal to n times n minus 1 factorial. Okay, so you can extend it more depending on the situation. So what we have here, the left hand side will be the same. We have x to the n plus 1 over n plus 1 factorial. N starts from 0 to positive infinity, but the right hand side, first term on the right hand side, should be expressed as this one here. Sorry, this is n plus 1 times a sub n times x to the n plus 1 n plus 1 times n factorial by using the definition. How about the second term? This will be the same explanation. This is x to the n plus 1 n plus 1 times n factorial. N starts from 0 to positive infinity, 0 to positive infinity. So what do we have here is we can cancel this one. This is multiplication, that one. Okay, so after simplification, so we have to put here simplify. So just copy the left hand side. We sub n plus 1 x to the n plus 1 over n plus 1 factorial, 0 to positive infinity. So this will become a sub n x to the n plus 1 over n factorial. N starts from 0 to positive infinity minus, we have here n minus 1 x to the n plus 1 over n factorial. N starts from 0 to positive infinity. Okay, so let's put it somewhere here. After you simplify, okay, so let's substitute. Notice that our a of x, sorry, a of x is in this form. So this is our a of x. Okay, this is our a of x. So please note that. So we will use that expression to substitute to this last equation. So note that the left hand side, this one here, left hand side, is so if you try to expand, this is a sub, when n is equal to 0, this is a sub 1 x to the 1 over 1 factorial, plus this is a sub 2 x squared when n is equal to 1 over 2 factorial. Let's try one more, x cubed over 3 factorial, okay, plus dot dot dot, so meaning to say, so the left hand side is, I don't know if you notice, a of x minus a sub 0, okay. So try to expand, as you have noticed here, this one here, we know that our a sub 0 is equal to 1, okay. So minus a sub 0, okay, you have to subtract minus a sub 0 here, so a sub 0 is equal to 1, so that what will remain is this expression, a sub 1 x to the 1 over 1 factorial, and as you can see here, this is the expression. So this is a of x minus 1, okay, since a sub 0 is equal to 1. How about the first term of note also? Note that the first term of the right hand side, first term, this one here, where are you, this one, first term, so let's denote this equation as star, okay, let's denote that one as star, okay. The first term of the equation star note that the first term of the right hand side is this is summation of a sub n x to the n plus 1 over n factorial. N starts from 0 to positive infinity, and as you notice, this is this can be written as you can factor out x here, summation of a sub n x to the n over n factorial. N starts from 0 to infinity, okay. Since I don't know if you get it, this one here, x to the n plus 1 is x to the n times x, so all the summands have the factor x, so you can factor out x in the expression. If you try to expand this one here, this expression, there's a common factor which is x, so With this in mind, we can write this one as x a of x. Okay, x a of x, because this expression, this one here, is a of x. If you go back to our assumption here, okay, so that's the first term of the right hand side of equation star. So how about the second term here, this one? How about this one? So let's try to solve it. Okay, note that the second term of the right hand side is, as you have noticed, this is negative of the summation of n minus 1 a sub, no, not a sub n, x to the n plus 1 over n factorial, where n starts from 0 to positive infinity. Let's look at here, this one here. Okay, n starts from 0 to positive infinity. We have x to the n over n factorial. So we have here. So let's distribute. This is very much easy to simplify. So this is negative of the summation of n times x to the n plus 1 over n factorial, plus we have summation of x to the n plus 1 over n factorial. N starts from 0 to positive infinity, 0 to positive infinity. So negative times negative, we have positive. Okay, and this the first term of this equation, this one here, the first term, second term, first term, second term, and this is the second term of equation star. This can be written as I don't know if you notice, this can be written as n times x to the n plus 1 over n factorial. N starts from 1 to positive infinity. Okay, why is that? The reason is that this term, because the reason for this is because 0 times 0 times x to the 0 plus 1 over 0 factorial is 0. Okay, notice that x to the 0 plus 1 is x. Okay, and we know that 0 factorial is 1. Okay, I don't know if you recall in the definition of this is the definition. 0 factorial is equal to 1. Just recall your statistics, okay, or combinatorial mathematics. So the first term when n is equal to 0, that's the first term is just equal to 0. So they are just equivalent. Okay? And the second term is we can factor out x. Okay? We can factor out x since the same argument as uh, as this one here, the same argument. So there is a common factor here, which is x. So this is x summation of x to the n over n factorial. N starts from 0 to positive infinity. Okay, why is that? Because if you recall your uh, calculus 3, we know that e to the x is equal to summation of x to the n over n factorial. N starts from 0 to positive infinity. Okay, we will use that idea. Okay, this one here. We will use this idea to substitute. That's why we write it in this form. Okay, we convert it in that form. Okay, so next is sorry, this one here. We write it in this form: negative summation of x to the n plus 2 over n factorial. N starts from 0 to infinity. Okay, why is this? Why do we need to write the first term as are they equivalent? Okay, sorry, notice that we can, sorry, this one here, this expression here, we can cancel out. We can use the idea, this one. Okay, replace n factorial by n times n minus 1 factorial. So from here we can where is the eraser? We can write n factorial as n times n minus 1 factorial. Okay, so we can cancel out this one here. Okay, and what remains is n minus 1 factorial. Okay, so this means that this expression, the first term is negative summation of x to the n plus 1 over n minus 1 factorial. N starts from 1 to positive infinity. Okay, that's it. And from here, this one here is just equivalent to this form. Okay, try to substitute. If you want to expand, let's try to expand this one here. Let's expand this one. This is minus, when n is equal to 1, we have x to the 1 over 0 factorial plus n is equal to 2, x squared over 1 factorial, x to the 3 over 2 factorial, and so on and so forth, up to this will become x to the n plus 1 over n minus 1 factorial plus dot dot dot. How about this one? This, okay, if we expand that one, this is, let's use this one, minus when 0, where are you, n factorial n is equal to 1, x to the n plus 1. Am I wrong? Okay, x to the n plus 1, I'm looking at my notes, x to the n plus 1 over n minus 1 factorial, and then so this one here, so it starts at 0 factorial, so this will become 0 x squared. Okay, this will become, sorry, x squared 1, sorry, this is x squared. Okay, I think I made a mistake, this is x squared. That is the reason why I wasn't able to get it. So this is x squared over 0 factorial plus x cubed over 1 factorial, x to the 4 over 2 factorial, and so on up to x to the n plus 2 over n factorial, dot dot dot. Okay, so I think I made a mistake somewhere here. We have, when n is equal to 1, n is equal to 1, we have 1 plus 1 is equal to 2. Okay, 1 plus 1 is equal to 2. Let's have this eraser, something here. Okay, so this is 2, and this is 3, this is 4. Okay, when n is equal to 1, when n is equal to 1, we have 1 plus 1 is equal to 2. When n is equal to 2, 2 plus 1 is equal to 3. And then 2 minus 1 is 1 factorial. So that's it. So they are, as you have noticed, they are just the same. The first term here, this and the first term here is can be written as in this form. Okay, and just copy the second term. So this is x to the n over n factorial, n is equal to 0 to positive infinity. Okay, the very purpose why we write it in this form is that we will use this this idea, this one here. Okay, so this is equal to negative of, we can factor out x squared, x to the n over n factorial. N starts from 0 to positive infinity plus, just copy, over n factorial. N starts from 0 to positive infinity. Just like before, you can write this one as x to the n times x squared. Okay, so every term, if you expand this the summation, if you want to expand the summation, every term has the factor x squared, so that's why you can factor out x squared here. Okay, so that's the reason. And finally, this is negative, sorry, this is negative x squared e to the x plus x e to the x. Okay, so that's it. So we are almost done. So equation star is equivalent to a of x minus 1 is equal to x a of x minus x squared e to the x plus x e to the x. Okay, this, where are you, equation star, this one. Okay, just plug in. This is a of x, the right hand side, this one here, a of x minus 1. The first term is x a of x, first term, this one here, and the second term is this one here, this one. Okay, this one. Okay, so let's simplify. We can write it as a of x minus x a of x 1 minus x squared e to the x plus x e to the x. Okay, so just transpose -1 to the other side, to the left side, to the right side, and x a of x to the left side. So let's factor out. Let's factor out a of x. This is 1 minus x, and on the right hand side of the current equation, this is, we can factor out x and e to the x. What remains here is we will have negative x plus 1. Okay, and we can divide both sides by 1 minus x. We can multiply both sides by 1 over 1 minus x. This one here also, we can multiply by 1 over 1 minus x. So we can cancel out this one here, and what remains on the left side is a of x, and the first term is 1 over y minus x. You can distribute this one here, that one, and also this one here. Notice that negative x plus 1 is the same as 1 minus x. So this will become where are you? This will become where are you? This should be, okay, sorry, this should be positive. This is positive. Okay, this is positive, that one here, because x times e to the x times negative x is negative x squared times e to the x. Okay, so this will become positive x e to the x. Okay, so that's it. This is the exponential generating function. This one here is what we call this is the exponential generating function for an. Okay, so to find the closed form, let's move at the top somewhere here. Where are you? This one here. Let's continue on this side. We know that a of x is 1 over 1 minus x plus x e to the x. Okay, so 1 over 1 minus x is, you know that already, this is the power series for the this is the geometric power series. Okay, x to the n, where n starts from 0 to positive infinity, but the right hand, the second term on the right hand side is the exponential function, okay, e to the x. This is x to the n over n factorial. N starts from 0 to positive infinity. And as you have noticed, the same argument, n is equal to 0. So what we will do here is the problem here is we have a variable x somewhere here, so we can distribute. So this is summation of x to the n. So what we need is we need x to the n. Okay, x to the n plus 1 over n factorial. N starts from 0 to positive infinity. And then we cannot combine these two because the first term, the exponent is x to the n, the second term is x to the n plus 1. So we are going to change the index. Okay, we are going to change the index to x to the n. So this one here, the exponent x should be x to the n, and the index will be changed also. So this is just copy x to the n, n starts from 0 to positive infinity, plus notice that they are equal to this one here, x to the n over n minus 1 factorial. N starts from 1 to positive infinity. So what happened? Are they equal? Remember that if you expand 0 factorial, we have 0 factorial is 1, x to the 1. Okay, x to the 1. This one here is, the first term is 0 factorial in the denominator. We have also here x to the 1, which is the same. When n is equal to 1, x squared, we have 1 factorial. When n is equal to 2, we have x squared, the same, 2 factorial. Okay, 2 minus 1 factorial is 1. So they are just the same. So we will put somewhere here the explanation. Okay, change the index so that we use x to the n instead of x to the n plus 1. Okay, so let's further simplify. We need a factorial. Okay, a factorial. So we will multiply by n factorial over n factorial. Okay, this one here. we know that n factorial divided by n factorial is 1. Okay, this is just the same as the previous term. Okay, this one here. So we need that so that since we are dealing with exponential generating function, plus this is summation of notice again that this is n times, okay, x to the n starts from 1 to positive infinity. Okay, they are just the same since n factorial is this one here. Where are you? This one. Okay, so we can replace n factorial by n times n minus 1 factorial. So cancel out, it will be the same as in the previous x term here. Okay, so let's further simplify. Notice also that the index start at n is equal to 0 here, and starts at n is equal to 1, so therefore we have to make it the same. So we have here, this is the first term is almost the same, okay, but the second term is not. Times x to the n over n factorial, n starts from 0 to positive infinity, and we know that this is just equal to, so there's so much tricks here, they are just the same. Why? Because the equality holds because we know that 0 times x to the 0 over 0 factorial is equal to 0. Okay, if you try to expand, okay, if you try to expand this term here, if you try to expand this, this is just the same as this one, because 0 times x to the 0 over 0 factorial is equal to 0. Okay, we are almost there. Sorry, we are almost there. We can this one are, sorry, they are just the same, this one here. Okay, so we can factor out, and also notice also this one here, they are just the same index. Okay, the same index, so we can simplify further as n factorial plus n times the quantity x to the n over n factorial. N starts from 0 to positive infinity. Okay, so we are almost done. Okay, since the coefficient of x to the n over n factorial in a of x is n factorial plus n. We have a sub n is equal to n factorial plus n. Okay, so this is the end of the solution, and as you notice, in this example, we write the closed form of a sub n in in our given, okay, as a closed form. Okay, so just replace n by n plus 1, then you will have this expression here. Okay, so that's it. I believe that you what they call this one, I believe that the method of generating function in solving the in finding the closed form or the explicit form of the recurrence relation is very useful and very amazing. Okay, so I hope that you learned something from this lecture, and also uh, I will leave the example 26 letter C and ND as your problem set. I will also uh, add at least maybe 2 or 3 more, okay, or maybe one, and doing the reverse also. If you are given the closed form, what is the given recurrence relation? I will uh, add one more problem set, that kind of the problem, okay, the reverse of what we did. Okay, so remember that you are given a recurrence relation using generating function, you arrive the closed form. But what if you are given a closed form, then find the recurrence relation? That's the reverse of the of what we did here. So thank you so much for um, taking your time to listen to this lecture. God bless. Okay, let's try to code example 26, those 5 problems, and also illustrate to you how to use the recurrence calculator. So before we encode the code, the Python code for recurrence relation, let's start with the code for the Fibonacci sequence. Okay, so let me open my Python IDLE. So let's go to uh, our desktop monitor and open the what do you call this one, Python IDLE. If you are using Windows, so you will see it something like this. So let's open a new file. No, not open a new file, but let's have a new file. Okay, so this new file, where are you, we will code the Fibonacci sequence. As you recall, I think this is the Fibonacci sequence. F sub n is equal to f sub n minus 1 plus f sub n minus 2. Our initial condition is f of 0 is equal to 1 and f of 1 is equal to 1. So let's try to code our Fibonacci sequence. Okay, first let us define our function. We will call this one as feb. No, not, let's say big F of n. Okay, we will denote our function, our sequence, as f of n. And then notice that based on our initial condition, that if it is 0 or n is equal to 1, then we have 1 1. Okay, or some some what they call this one, some books use that f of 0 is equal to 0 and f of 1 is equal to 1 as the starting value. Okay, so if n is equal to is less than or equal to 1, is equal to 1, we will return n. Okay, and else we compute the formula. Okay, so return our formula is f of n minus 1 plus f of n minus 2. Okay, then let's define the terms of the sequence. Okay, so for example, if you want the 10th term or if you want the 11th term, example n term is equal to 10, you want to know the 10th term, then first is we have to check if the term is valid. Okay, if this means that if it should be, the term should be a positive number. Okay, or 0, including 0. Okay, so if n terms is less than or equal to 0, okay, if it is negative, then we have to print this code here. Please enter a positive integer. Okay, if it is a negative number, else we will evaluate, okay, this return here. Okay, else print Fibonacci sequence. Fibonacci sequence is, okay, I know that you are familiar with this. For I in range terms, okay, n terms, okay, we are going to print the sequence f of I. Okay, so then we are going to first is to save. Okay, save the file as let's say feb n. Okay, that's it doesn't matter how you name it, and then you're going to click the run or F5, and you will see the what do you call this one, the sequence. Okay, so there are 10, 1 2 3 4 5 6 7 8 9 10. Okay, so let's try, let's say let's try -2. Okay, Uh, okay, so it says here, please enter a positive integer. Since n term is equal to negative 2, as you can see here, it is less than or equal to 0, then it will print this one here, please enter a positive integer. How about if we have 0? Okay, so greater than or equal to 0, let's run. Okay, please enter a positive integer. So we know that 0 is not uh, positive, so we have to run. How about 1? So we have 0. Okay, so since 1, the in term is 1, so we do not in the range function, uh, since n term is equal to 1, it will evaluate 0. Okay, and it says here, if it is 0, 0 is less than or equal to 1, it will return 0. Okay, this is 0 here. Okay, so which is different from the formula. As you can see in the formula here, as I've said before, there are books that uses the first term is 0. Okay, so what if it will start at 1? Okay, and the second term is 1. So how will you code the Python code for that case? Okay, so that will be uh, your assignment. Okay, that's one of your assignment. uh, Code the Fibonacci sequence if it will start at 1. Okay, and the second term is 1. Okay, so we have 1 1, so you can say 1 1 2 3 4, and so on and so forth. Okay, so in this code, we use the idea that f sub 0 is equal to 0 and f of 1 is equal to 1. Okay, so as your assignment, uh, this will be your assignment. Okay, uh, start at f of 0 is equal to 1 and f of 1 is equal to 1. Okay, and generate the Fibonacci sequence. So that's how you are going to code the Fibonacci sequence. Okay, I'm sorry, I think I wasn't able to show you in the open in the in the uh, in the PDF. Okay, so as I've said, once again, there are books that it will start at 0. So and then the next term is 1. So in the code that I've shown you, it start at 0 and the second term is 1, but here in example 1.2, it start at 1 and then the second term is 1. So as in your assignment, make a code, Python code for Fibonacci sequence that start at f sub 0 is equal to 1 and f of 1 is equal to 1. Okay, so it should be that the first term here is, the first and second term must be 1 1. That's your assignment. Okay, so let's try to use the calculator. Okay, calculator. Let's try to use the recursion calculator to generate the sequence. the Fibonacci sequence. So you can use any. Okay, how to use this calculator? It says here that the term for n minus 1 term is v. Okay, v. For n minus 2 is w. For n minus 3 is x. For n minus 4 is y. And for n minus 5 is z. Okay, there are how many terms? 1, 2, 3, 4, 5 only. Okay, and then for Fibonacci sequence, this is the formula. V is equal to v plus w. V is n minus 1 and w is n minus 2. Okay, plus. So the first term is, it says here 1 1. So let's calculate. We have here 1 1, so on. But if we start at 0, okay, and calculate for you, what happened? 0, number of start values is 0, and then number of recursion, let's say 11, and let's calculate. So start at this one, 0 1. Okay, how about if we go to our example 26. Where are you? This one here, example 26. Let's try letter B. Okay, 5an minus 1 is minus 6an minus 2. Okay, so let's go to our calculator. Let's reset this first, and then start with 0 1. So 0 here, and then we have 5 times for multiplication is asterisk 5 times rn minus 1 minus 6 times n minus 2. Okay, let's try to calculate. So this is the sequence. Okay, I don't know if this is correct. So it's when n is equal to 2, let's go back here. N is equal to 2, let's say 2 a sub 2. 2 minus 1 is 1, so 1 times 5. Did I make a mistake here? 0. A sub 0, 0. So that it should be a sub 2 must be 5. So what happened here? I think there's a mistake for this calculator. Okay, there's a mistake. 0 1. So what happened? Did I make a mistake? Minus 6 rn minus 2, n minus 2. So what happened to the code? Okay, so I think there's a problem. I don't know what happened. So maybe let's try again. 5 times minus 6 times. Maybe let's put a parenthesis somewhere here. Parenthesis. Okay, so that it will evaluate the multiplication first. Okay, and then let's evaluate, calculate. Okay, so what happened again? 1. I know this is 0. This is 0. Okay, calculate. Oh, number of start values is 2. So I think there's a What happened? Okay, I think there's a mistake with this code, with this calculator. Maybe let's ask the author of this website, why is it that there's a mistake. Okay, let's calculate. See, so 0 1 0 1, we have here 0 1 and then a sub n minus. There's a mistake somewhere. Okay, anyway, let's try again another one. Let's try, how about this one here. How about letter A? Okay, replace n by n minus 1. So 2 times 2 times n minus 1, 2 times plus 1 here, and should be 1, sorry, it will not allow to evaluate only one recursive variable. Okay, so let's try another. Let's try this one here, is letter D. Replace n by n minus 2. Okay, anyway, just replace n by n minus 2. So let's open our open board first. 2 F2, where are you? Sorry, I think I already disable my what do you call this one, open board. So anyway, in this example, just replace n by n minus 2 here, n by n minus 1, and adjust the starting values. Okay, so that's how you are going to use this calculator. I don't know what happened, but I think there's maybe a mistake on our part, or I don't know. Just try it at home. Just copy this what do you call this one, just copy this where are you, copy this URL in the Google browser, and then make use of this recursion calculator. Or you can try any what do you call this one, just search in the Google for a recursion calculator. Okay, so but if not, use a code. Okay, Python, just code the what do you call this one, just code the recurrence relation. Okay, if you ask for a Python code for generating function, maybe you can search it in the net if there is any, but if not, use your part 0 knowledge when coding the generating function. Okay, so thank you so much for listening. I hope you learned something in this lecture video. God bless everyone. Hello, I found a calculator. As you can see here, F3. This calculator, let's say this one here, I guess the calculation is wrong when we tried before, but I found calculator from Wolfram Alpha, and this is the one here. Let's open this one, and for example, if you have this one here, let's click this option here. So we have uh, the recurrence relation for this is not Fibonacci. So let's start with f of 0 is equal to 0, f of 0 uh, and f of 1 is equal to 1. So enter, and this is the Fibonacci number. Okay, so for example, if you want to get the sequence, the elements of the sequence of letter B, example here, you can put it somewhere here, like a sub n is f of n. So we have 5 times f of n minus 1, or a sub n minus 1, minus 6 times f of n, or a sub n minus 2. And the initial condition is the same, so let's click that one, and as you can see, we have the same answer. Okay, this is the right one, and this is the graph of the sequence. Okay, so how about let's try, I guess this is the correct calculator. How about example 26a, 2a sub n. So let's try this one here, n plus 1, n plus 1, and then 2 a sub n plus 1 here, plus 1, and the initial condition is a sub 0 is equal to 0. So let's delete this one here and click this equal sign, and as you can see, this is the answer. F of n is equal to 2 to the n minus 1. Again, we are correct with our solution. So I guess this is the right calculator. You can type in the Google browser like recurrence relation calculator, and the first one that will come up here is the Wolfram Alpha. So you can use this one as a correct calculator. This one is, I think, it will work only for positive. If all the what you call the linear combination of those n minus k variables is positive, if you will use plus sign. But if minus, I think this is, I don't know what happened. So I anyway use this one, Wolfram Alpha, to know if your answer is correct, the closed form is correct. Okay, so I guess this is the correct calculator for recurrence relation. Okay, thank you once again. I'm sorry for adding this video. I feel uneasy because the first calculator that we use is not working well. Okay, so God bless everyone. Try also for the other sequence, or if you have a sequence in mind, or if you have sequence in a book, okay, in a given book. Okay, try this sequence. Okay, so let's end this video. and thank you for listening.